A very common Calculus 1 problem is where they will provide you with the derivative of some unknown function and then ask you to retrieve the original function. And so in this video, I'm just gonna work through and it's kind of a simple example, just explaining the idea behind it and how it works. And then in the next video, we'll do some more difficult examples. But for this one, here we go. We're asked to find little f of x if we're given the derivative 3x squared minus 5x plus 2, as well as what we call an initial condition. F of 2 has to be equal to 1, and I'll explain why that's in there in just a minute. Okay, so the first step should be somewhat clear. If we're given a derivative, to get the original back, we're going to have to integrate because, as we should already know, integration and differentiation are, in some sense, inverse operations of one another. One undoes the other. And so if we want to get little f back, we would take the integral, the indefinite integral, that is, of 3x squared minus 5x plus 2 dx. And this integral will be x cubed minus 5 halves x squared plus 2x. And then we have this plus capital C. And we remember this guy from studying indefinite integrals. We always have this plus C on the end because we could have any generic constant there. And when we're checking his derivative, that plus C, no matter what it is, would go to 0. It would not be in the derivative, right? Because the derivative of any generic constant would be 0. So now that's actually the problem is we don't have a specific function. This is thousands of functions. I mean, actually it's infinitely many functions because as the C changes, we get just different function after different function. So that's where this guy comes in. That's where this initial condition becomes helpful. And this says that if you plug in 2 for x, we should get out 1 for y. To say it another way, this function here should go through the point 2 comma 1, where 2 is the x and 1 is the y. And how do we know that? Well, it should be clear, but this is f of x, and so the x is 2, and then f of x, the function evaluated at 2 is the y value, which would be 1. So let's plug in 2 for x and 1 for y. If you plug in 1 for y, the function would be 1. 2 cubed is 8. 5 halves times 2 squared would be 10. Plus 2 times 2 makes 4. And then plus capital C. So this gives us an equation right here that we can actually solve for capital C. We can find the specific C value, the specific constant that lets our function up here that we found earlier satisfy the appropriate initial condition. So 1 equals 8 minus 10 is negative 2. Negative 2 and 4 make positive 2 plus capital C. So sure enough, C is negative 1. C is negative 1. All right, now what do we do with this guy? Well, we use it to write our final answer. So our final answer would be this. It was basically little f up here. I mean, this was basically our function, only at the time we did not know what the plus C was. Well, we just found it. Okay, so our final answer would be little f of x equals x cubed minus 5 halves x squared plus 2x minus 1, and the reason I know this is correct is it satisfies all the conditions. On the one hand, and you can check me on this, f of 2 really does equal 1. In other words, you can plug 2 into our function and you would get 1 out, as well as the derivative is this, right? And so it satisfies not only the derivative stipulation, but the initial condition stipulation as well. So that's how we do it in short. You find an indefinite integral that has a plus C in it, and then you use the initial condition by plugging in that x, y value into your function to solve for capital C. Once you get capital C, you plug it in and you're done. Now, just a little extra. I mean, you're welcome to move on to the next video, but let me explain what's going on here behind the scenes. See, what happens when you have an antiderivative with the generic plus c on the end, you actually get a whole lot of functions, right? This is a family of functions. And as we said earlier, the derivative doesn't depend on the c. You know, notice if you choose a particular x value, the derivative is the same for all of these guys, regardless of what our plus c is. So that makes it very difficult to nail down one particular function. So what we need in order to nail down one particular answer is that initial condition we talked about. So somebody might say, okay, your function has to go through this point right here, this xy point. And then once that's decided on, then it's very straightforward. You can use that to your advantage and find the particular function that is the same main antiderivative as the rest of the guys, but the plus c is chosen to slide that function up or down to snag that initial condition, or in other words, to go through that initial condition specifically right there. And that it excludes everybody else. So that's a little bit of why it works, and so hopefully that makes it a little bit more clear to you. Now we're going to move on and try some slightly harder examples in the next video, where maybe we're starting with the second derivative and two initial conditions where we have to trace it back to the original function.